Welcome back, friends. Good evening, all. This is a continuation part, okay? Without any waste of time, let us start the session. See the dynamic conductance. So many students have given the correct answer, it's okay. But the dynamic resistance, you know, RD is equals to eta Vt by If, forward biased current, okay? Automatically dynamic conductance will be proportional to current. So directly proportional to the current. Dynamic resistance inversely proportional to the current. Okay. Depletion layer is found in. So the depletion layer, what exactly the meaning of depletion layer? It is actually an insulating layer or isolation layer due to recombination of electrons and holes. Okay. So whenever or wherever the junction is found, there we can see the depletion region. Not in p-type semiconductor, n-type semiconductor. Their combination is nothing but what? Diode. Okay. Avalanche break is primarily depends on the phenomena of see avalanche breakdown. Avalanche breakdown occurs in PN diode. Do you remember? Try to collect more number of objective bits from here. In PN diode, due to as you keep on increase the reverse bias voltage, so due to the cumulative ionization, right? So the collision will take place. So the primary reason here, whatever the less number of minority carriers or electrons we have, these electrons can collide with the ions. It's okay, right? So slowly, due to the increasing the number of carriers, finally the device enters into the catastrophic effect called avalanche breakdown. In Zener diode, Zener breakdown occurs. In PN diode, avalanche breakdown occurs. In transistor, punch through breakdown occurs. I have given 3 objective bits. Okay, 3 objective bits. Okay, let me take it as a question number 1. Okay, let me verify answers. Please type your answer. Okay, please type your answers. Avalanche breakdown. What kind of breakdown occurs here? Avalanche breakdown. Breakdown is avalanche breakdown. But he is asking about the region. So I am unable to, I think maybe problem is from my side. Okay, I am unable to connect to the live. Please, I will retry it. Give me 2 seconds time. I can't see any reply. Initially I have seen one reply only. Just give me 2 minutes time. Meanwhile, you can think about it. Okay. So it's okay. It's mainly depends on, let me give you the answer, right? Collision. So collision is a primary level or primary step in the breakdown, strictly speaking, right? Due to the collision of our cumulative effect. This is the collision, okay? Cumulative effect. Okay. Impact ionization also correct. Impact ionization is also correct. Okay. But doping, it's a completely different story. Recombination, ionization is different story, okay? Ionization is different. It is not at all belongs to the breakdown, right? Now, I've seen that one student given that option, collision, I think option B, immediately that option, that message was disappeared. And actually it is a open channel source, okay? So that's why I could not give my number, okay, because some students asked in yesterday's class, right? The team was given that instruction. I don't have the permission to give my number on the board, of course. And the students who are having the ACE online app, okay, you can contact me through the ACE online app. Okay, ACE online app, you can have directly the name you can send me a message, you can see the reply. There also you can find PDF notes, everything. Even you can download it if you are not registered yet, no problem, right? Voltage across a Zener diode. Already in, I think yesterday's class we have discussed constant in forward direction, constant in reverse direction. Do you remember constant in reverse direction? And look at this, look at this. You better to read all the options. Constant in both forward and reverse direction. This is the dominating option because Zener diode operating in reverse bias, 100% true, no doubt. This is VZ, okay? But in forward bias also, the voltage V gamma around 0.7, same as normal diode. It is also constant, okay? It is also almost constant. As whatever the Zener diode voltage stability we have, the same stable voltage drop across the Zener diode in forward bias also possible, but that value may be very less. He is not asking about the value, okay? So, constant in both forward and reverse bias, right? So, C is the correct option. I am going for the next question. Which of these has a highly doped P and N regions? I think I don't want to give any discussion. I have given in yesterday's class, okay? Can I go back? In yesterday's class only we have discussed it. It's okay. I think you guys can guess it very easily. The heavily doping profile you can see in the tunnel diode. PIN diode is different. PIN diode is different. P-type, N-type and intrinsic layers. So, high frequency variable resistor. Okay, answer 2 questions. Let us go for answer 2 questions. Okay, just it takes 10 seconds extra. PIN diode. P-type, N-type, in between there is some intrinsic material, of course. So, it is high frequency. It is one of the application of this diode. Diode is a high frequency resistor. And high frequency applications. Okay, so in the high frequency applications. So, based on the frequency, of course, here we can also use it as a capacitor also, strictly speaking. The PIN diode, it is a type of diode, right? In the diode classifications, we have discussed about PIN diode, gun diode, Leo-Esaki diode. Leo-Esaki diode is nothing but this Schottky diode, okay? Right, photodiode. Photodiode, this is little different. So, whenever this will convert light energy, okay, photon energy into electron energy. This photodiode, phototransistor operations are same. Symbol will looks like this. Schottky diode is different. It is high frequency switch operation purpose we are using. The recovery time of Schottky diode is very, very less. That's why high speed switch. High speed switch. In switching circuits we are using this. One more important point. Schottky diode is like a metal to semiconductor diode. Metal to semiconductor. We don't have junction in Schottky diode. There will be a metal and P-type semiconductor, like, okay, metal to semiconductor diode, right? And so this is actually a high frequency switch. Recovery time of Schottky diode is very, very less. For example, you might have studied maybe in diploma or in BTech, TTL logic, transistor logic. There only you might have studied Schottky TTL, okay, high speed transistor logic. Actually, we are using the Schottky transistor. Schottky transistor, again we can implement with the help of Schottky diode only. So, that is the story. At least if you recall this story from our discussion, you can answer some of the questions in future. PN junction diode in reverse bias, current is very, very less. Okay, you just choose the option amperes wrong, milliamperes, amperes wrong, micro to nano. Strictly speaking, that guide should give nano to micro. It's okay in the order of few nanoamperes to microamperes only. D is the correct option. I no need to wait for your option, okay? Direct question only, na? That's why. Number of doped regions in PN diode. Immediately students are selecting one. Read the question, man. Number of, is not asking about number of layers, number of doped regions, okay? Number of doped regions. P-type and N-type. Doped with trivalent impurity, N-type doped with pentavalent impurity. Okay, anyways, 2 doped regions. Depletion layer width of junction. Depletion layer width of the junction decided by so many factors, of course. If doping concentration is high, width of the potential barrier width will decreases, low. Inversely proportional to doping concentration. This is the extra bit I am giving you. Take it. What is the answer for this? He is given that doping decrease with the light doping. No. Decrease with high doping, okay? Inversely proportional. I said inversely proportional. So this is wrong. Independent of applied voltage. How can I say that? No. Increase under reverse bias, increase with heavy doping. Increase with heavy doping. No. If the doping increases, then width decreases. Inversely proportional, I said, okay? Decrease with heavy doping, then it would be correct answer. Increase with heavy doping is wrong answer. The leftover is increase. You know that here in reverse bias, okay? The reverse bias voltage increases, potential barrier width will increases, no? That's a quite common point. So that is not my intention. If my intention is to give answer for this question, directly I can say reverse bias increase, I can give the answer. I want to give extra information. So potential barrier width will increases if the reverse bias voltage increases. Potential barrier width decreases, okay, if the doping concentration increases. If doping increases, potential barrier width decreases. Okay. Let me go for the next question. I'm sorry, I could not connect to this, right, to some problem I think. It's okay. Right. Going for the next question. PN junction diode is RLC, resistor, inductor, capacitor. These are the passive elements. It's not at all a vacuum tube, of course. Unilateral, bilateral. Unilateral. What does it mean by unilateral? It allows the current only one direction. One direction, unidirectional device, okay? So, means the conventional current is always flow from anode to cathode. That's why, right? That's why it is a unilateral device. Schottky barrier diode. Do you remember just now I have given? No PN junction. Schottky barrier diode is not having any PN junction because look at this man. No PN junction. No PN junction. Common sense here. What I told you, there is no concept of P-type and N-type materials in the Schottky diode. Metal to semiconductor. So this semiconductor is of course P-type. Metal to semiconductor. We have metal and semiconductor. We don't have P-type and N-type semiconductors. Okay. Then how can I get a P-N junction here? Okay. We don't have separate N-type material, N-type and P-type materials in Schottky diode. We have metal, of course. Generally we are using aluminum, whatever may be, metal to semiconductor. Generally semiconductor is P-type. We don't have P-N, P and N elements in this diode. That's why no concept of P-N junction. So little tricky question. You should understand it carefully. 95% of the students selected one PN junction. Okay? No? There is no concept of P-type and N-type material. Both P and N-type material in Schottky diode. It is a metal to semiconductor device. Isaki diode, of course, also called as. The connection of Zener diode in circuits always, already we have discussed, okay, reverse biased. Strictly speaking, all options are provided reverse bias. Strictly speaking, the very 100% the correct option, correct format of this particular statement is reverse conduction state. But we don't have reverse conduction in reverse bias to go for a priority. He has given positively biased series forward like that. Reverse bias is a suitable answer. Reverse bias, but in reverse conduction state only it can act as regulator. But to bring it into reverse conduction state, first of all it should conduct in reverse bias, na? That's why reverse bias is correct. Why? He is asking Zener diode in circuit is always. He is not asking Zener diode act as voltage regulator in. If question is Zener diode act as voltage regulator in, then correct answer is reverse conduction state only or reverse breakdown state, right? but it is how it is conducting means obviously reverse bias. Then only we can bring it into reverse conduction state. That's why B is a suitable option. Some information from transistor circuits. For stabilizing the gain of an amplifier, you know, we have discussed in feedback amplifiers. Some students, of course, from the self-phased program, they have been sending the messages, sir, nowhere in the syllabus feedback amplifiers mentioned, but you have given around 1.5 hours of feedback amplifiers video. Sir, do I want to watch? Once if the video is available in our course, you must watch it. You must watch it. Otherwise, why the people, I mean our team will provide that video extra lecture? Okay, they don't provide it for free of cost now. So that you should understand. Once if that particular topic is available in our course means you have to go through that course, that particular video or topic, okay? Right, even though it is not given in syllabus. You can find in GATE syllabus, ESC syllabus, PGA set syllabus, or like Mahatransco syllabus, AP and TS Genco Transco syllabus. But in this RRB JE you don't have feedback amplifiers. They did not mention it clearly. But questions are found, not only 2014. I have seen that so many questions are found from this area. That's why I made that video, okay? Feedback amplifier. What was the classification here? Positive feedback, negative feedback. Positive feedback used in, I'm recalling the concept. Positive feedback used in oscillators and multivibrators and Smith trigger also. Negative feedback by default students can give easily, the answer is amplifiers. So why should I use negative feedback? Stabilization. To stabilize the gain, we should use negative feedback in amplifiers. So negative feedback, C is the correct option. Negative feedback. Common base configurations. Common base configurations. See guys, you please try to attend each live session. And or otherwise the best idea is after live, if you go through the video, you just watch it at 1.5x speed. You better to take screenshots, that simple task, okay? Please, but these are the selected questions. Actually these questions are not taken randomly from previous year. Without repeating the questions, we have some idea, of course. We have our intention is different, our ideology is different. It's in a systematic way, generally faculty select some questions. So definitely these questions will help you not only to recall the data in exam also. So that's why I'm not going to give any confirmation this question is going to give, but this question relevant information you will definitely see in the exam. Okay, right. So that's why in every subject, just you take the full screen, you take the screenshot, better, right. Common base configuration refers to the configuration of a transistor here, common base, common emitter, common collector. And this question is also common. Okay. Based on choice of Q point. Q point means operating point. DC operating point, strictly speaking. The current voltage characteristics of the transistor. So it's about BJT. Amplifiers classified as. So based on the operating point, do you remember guys? See, exactly at the center of the DC point. Of course, it is an intersecting point of AC and DC load lines. It's okay. So based on this VI characteristics, we are selecting the Q point. So different classifications means definitely it's a power amplifier. But small signal amplifier means voltage amplifier. Always it is at linear portion, piecewise linear operation. Do you remember? But for large signal amplifier, I mean power amplifier, we will have different operating points. Different Q points means by default your brain should go to the power amplifiers concept. Class A, this is class A, okay? This is class A. Do you remember mine? Class B. Somewhere here class AB and this is class C. That's all. These are the signal amplifiers. Class S and class D are pulse amplifiers. Pulse amplifier should not be considered like as generally power amplifiers or large signal amplifier. Large signal amplifiers, we are talking about this. Okay, C and D are different cases. Completely it is out of the box. It's a pulse amplifier. Okay. Class 1, 2, 3, 4, no, not like that. A, B, C and D, no. 1A, 1B, wrong. This is also wrong. You just your mind will swing between C and B. So by look at this, the most popular amplifier is class AB, of course, you know, right? So of course, that AB is included in option B. A, B, C and AB. Sir, why don't you select D? Here AB is missing. Next, D is a pulse amplifier, D and S. We should not consider them. That's why reasonably the B, class A, class B, class C and class AB are the classifications of the amplifier. Transistor amplifier are in these classes according to this particular topic. These are the power amplifiers or large signal amplifiers. Power amplifiers are large signal amplifiers. Right, guys. Now, yeah, please read the question. Right. The MOSFET switch in its on state may be considered as, see guys, once if the MOSFET device is operating, you know, metal oxide semiconductor, metal and oxide in between semiconductor. Do you remember the operation we have discussed? Source, rough sketch only, okay, source drain, SiO2 layer, then the gate, and here channel will be developed, enhancement type, example. So it is just almost like a capacitor. Between two metals there is a insulating layer or isolation layer, SiO2 layer, okay. So basically it is a capacitor. That's why we have discussed MOS capacitor, right? MOS capacitor is a basic, of course, MOSFET works on the principle of capacitor operation. And I have explained positive charge, electric line, negative charge, electric lines, how they influence the internal channel width, right? These things, and pinch off, channel pinch off, everything is almost like a capacitor operation. Okay. Direct question, it is a PNP transistor, na? This is NPN. Arrow mark inside, this is a PNP. And PNP transistor. PNP transistor. Zener diode symbol, you know, power diode symbol, NPN, of course, just it is like a normal diode symbol. Transistor, NPN, PNP are there on board. FET is a device which has a, look at this man, FET, field effect transistor. That means there are some common points. If you find FET, the points are belongs to JFET as well as MOSFET. Do you remember this? So for all of them, maybe JFET or MOSFET, values may be different. Even I have given the values also. Input impedance of JFET transistor generally, op amp, ideal practical conditions, MOSFET value, how it is changing, right? 10 to the power of 7, 10 to the power of 14, 15, MOSFET case 14, 15, like that I have given. It's okay. So for the FET, you remember this? Maybe JFET or MOSFET, okay? General points, you remember. Input impedance is very high, China. Input impedance is very high. Next, it is a voltage controlled current source. Gate to source, we are changing the gate to source voltage. Due to change in gate to source, we will see the change in drain current ID. ID equals to IDSS into 1 minus VGS by VP whole square, okay? So ID is equals to something into VGS, like VGS, gate to source voltage will decide the ID, drain current, or IDS, drain to source current. Next objective bit I am giving you. In FET and MOSFET, generally gate current is 0 under ideal conditions. JFET junction, here gate is reverse biased, so current 0. Always source current is equals to the drain current, okay? So these are the extra points. You have to remember, please recall them. Not exactly, highly impossible to recall that much of big subject just in 1 to 2 minutes. Okay, in the speed I may miss some points, that you have to understand, you revise the notes. Okay, I can give some hints only. What is this question? FET is a device which has high input, low input wrong, low input wrong. Okay, high input impedance and current control, high input impedance and voltage control. Look at this, it is a voltage control current source. What type of controlling? Voltage controlled. So high input impedance and voltage controlled. C is the correct option. In yesterday's class, one student, I think Kiran, someone asked me the FET based questions. That's why I have selected more, all the previous year FET based questions. So I cannot say this is MOSFET or JFET. He has given the question as FET, valid for JFET or otherwise, MOSFET. Okay, right guys. High input impedance and voltage control device. Next question. Which type of a gain is achieved using common base? Common emitter, common base, common collector. Common emitter, we can achieve both current as well as voltage gain. Both are high, right? Common base, voltage gain is same as a common emitter, you know. Even equations also, except the polarity, voltage gain relations also almost same in CBCE. But in current gain, common collector voltage gain is 1, nearly 1, practically less than 1, ideally equals to 1. But current gain is high, gamma. Okay? So common base, I have given 3 objective bits. And for this question, what is the answer? Common base gives voltage gain. Which type of gain? Okay, common base means voltage gain. That like very simple, straightforward questions. Right. Next, sometimes in the flow, okay, I may give one answer, I may select another option, right? Okay, please you observe it. I have given tick mark on B, voltage gain, common base. Please verify the question. Common base, common emitter, common collector. Otherwise, you can take screenshots later, okay? I'm going for the next question. A transistor has current gain of 0.99. In common base, very good. Do you remember? During the lecture also, I have given this point, I was highlighted this point. If I give current gain equals to 120, how can you decide? The current gain belongs to CE, CB. You cannot decide it, highly impossible. Okay? So, you should understand that. What kind of configuration is this? So, in common collector, amplification factor means gamma. Common base, amplification factor is alpha. Common emitter, amplification factor is beta. Okay, right. So, he is asking about the current gain in common collector. Current gain is asking in common collector. What an interesting question here. But silly question, okay, simple. In common collector, what is the current gain? Gamma. What is the gamma? Generally 1 plus beta. The known, very known equation. He has given what? Current gain in common base. But what is the current gain in common base? Do you remember? Current gain in common base, alpha. Alpha. But we have formula for the gamma. Gamma is nothing but current gain in common collector is equals to 1 plus beta. But beta is amplification factor in common emitter. Don't worry. We have a relation. Do you remember? Beta is equals to alpha by 1 minus alpha. This relation will help you. So, gamma is equals to 1 plus alpha value is how much? 0.99 divided by 1 minus 0.99. Please someone calculate it, okay? Gamma equals to 0.01, 1 minus 0.99, okay? 0.01, 1 by 0.01. So that 100 into 0.99 is how much? 99. 99 plus 1, gamma value 100, okay? Yeah, gamma value 100. A is the correct option. A is the correct option. Please verify. Enhancement. See, MOSFETs are basically classified into two types. Do you remember? EMOS and DMOS, okay? I have given this classification also. Just basic idea and basic classifications. Enhancement MOS and depletion MOS. Enhancement MOS, initially no channel available. Depletion MOS, initially channel available, like that, okay? Anyways, for the given question, enhancement is a word, okay? Is related to MOSFET, not about tunnel diode, photodiode or varactor diode. FET is a, you remember, do you remember just now? I can't go back here. FET, look at this. Basically, okay, basically not in closure loop. With the feedback, again control operation will be different. Shunt, series, shunt, that is different. Basically, if you take transistor, current control, current source. FET, voltage control, current source. Okay, right. Voltage control, current source. Going for the next question. Early effect, interesting question. Early effect in BJT. You type the answer for just randomly. I am giving question number 20, just randomly. For your comfort, you can answer question number 20, answer is like that, okay? Please go through it. Early effect. We have discussed the early effect. Early effect is different. Avalanche breakdown is different, okay? And Zener breakdown is different. Thermal runaway is different. Indirectly, by mistake, I have given answer now. Okay, it's okay. You try to think about it. Come on, my dear friends, please think about it. And I can't see your options because here, actually, this is a dead zone here. So, no signals are allowed, I think. I'm not able to catch your messages. Let me verify it again. Okay. Early effect in BJT. Listen, China. Avalanche breakdown occurs in, do you remember? Diode. Related to diode. Zener breakdown related to Zener diode. Thermal runaway related to BJT, but while you are increasing the VCC, I mean reverse bias voltage, okay, in the transistor, or otherwise due to temperature, increase in temperature, IC not increase, IC increase, again temperature increase. Do you remember that? I have explained that, okay. Then due to that cumulative effect, transistor enters into deep saturation and the device will damage. This just rough sketch only. We have spent around half an hour only on thermal runaway concept, okay, but the rough sketch. So this is the thermal runaway concept. What about this early effect? In the base, actually early effect means, do you remember early voltage? Like this I have given. So if you keep on increase the reverse bias voltage, what will happen? The effective base width will decreases. Base width will decrease. As we keep on increase reverse voltage, this thermal runaway we have discussed based on temperature, okay, purely. Here I have written temperature. I will write it. Temperature increases, IC not increase, IC increase, finally thermal runaway occurs. But what about the early effect? So according to the early effect, as you keep on increase the reverse bias voltage of the junction to collector to base junction, the potential barrier width will increases, and base is already lightly doped material and thin. That base width further decreases. So beyond certain value of reverse bias voltage, total base will be vanished. Then again device enters into catastrophic effect. Okay, so that is a situation. That phenomena is generally known as early effect. Okay, so base narrowing, or in nodes I have given it as base width modulation. You go and read it. Okay, base width modulation means change. Okay, because base width will decreases as you keep on increase that reverse bias voltage. So that is nothing but base narrowing. Concept same, he has given just different keyword. We have discussed this topic already in the self-phasor program, right? So A is the correct option. Two basic types of FETs are N channel and enhancement and depletion. We don't have. So in enhancement and depletion again N channel and P channel FETs are available. FET, MOSFET, in all different categories we have N channel as well as P channel. In transistors we have NPN and PNP. Okay. Unity gain amplifier. Do you remember, guys? Unity gain amplifiers are also called as voltage followers. Common collector is example. Voltage follower or voltage buffers. Example, common collector is one of the example. Voltage follower. See, power gain value given in dB. For example, this is for power gain in dB in decibels. Okay, we should use 10 log the power gain value AP, or he has given 50. Voltage and current gains we should use 20 log. Of course, it is based on, right, 20 log. For power gain we are using 10 log. For voltage and current gain we will use 20 log here. Of course, belongs to the network theory also, don't worry. 10 log. Ideal op-amp specifications. Do you remember? Input impedance infinite, output impedance 0, CMRR infinite, slew rate also infinite, differential gain also infinite. Ideal, I have given all ideal specifications. He is asking only input impedance, right? Input impedance infinite. CMRR, just now I have given somewhere here. CMRR, yeah, this one, infinite. Ideal case, okay? Right. Transistors are used in digital circuits. They usually on and off, saturation and cutoff. In digital, on and off mechanism we are using. Okay, that means saturation and cutoff. Large signal amplifier means what? Power amplifier. In yesterday's class I have given class A, class B. Today's class A, class B, class C, class AB, all are power amplifiers, are also called as large signal amplifiers. Negative feedback. Negative feedback improve, okay, improve the stability, but decreases what? Gain. Gain will decreases. Decreases in voltage gain by default, okay? Decrease in voltage gain. Right. The voltage levels for negative feedback, negative logic system. Negative logic system. It is belongs to DLD, digital logic gates, digital electronics. In the negative logic, our assignments of binary vector is different. High voltage assigned for logic 1 in positive logic. High voltage indicates 0 for negative logic, but we don't have specific voltage levels, okay? Remember, Must be necessarily positive, must be necessarily negative, could be negative or positive, must be necessarily be either 0 or minus 5, not like that. Could be negative or positive, no problem. 0 volts minus 5 volts I can take a logic, or plus 5 volts 0 I can take a logic, plus 5 volts minus 5 volts also can be separate as logic 1, logic 0. But how we are assigning levels, logic levels, that is decided by positive negative logic, we have discussed in digital electronics part. Okay. Could be negative voltage or positive voltage, not like that. Zero level detection. Zero level detection means, for example, okay, see, I am giving one signal here. So I want to detect the 0. Whenever the 0 is arrived, output should be 0. I can connect 0 here. This is nothing but what? Comparator. It is a comparator, okay. So there are two diodes, silicon and germanium, high voltage. Which diode will conduct quickly? Delicated diode. Which one is delicated? Germanium, right? So that germanium diode only conducts here. What is the cut-in voltage? 0.3. Right? He is asking about voltage across the 1 ohm resistor. Here what will be the voltage? This 5 minus drop, 5 minus 0.3 is equals to 4.7 volts. 5 minus 0.3, 4.7 volts. Germanium conducts, not the silicon, okay. If both are silicon, then 0.7 will be the drop, okay. But one germanium, one silicon means, so low delicated diode, strictly speaking, there is a technical, it's not a technical word, just for comfortability, we are using delicated diode, strong diode like that in the lectures, right. So the germanium requires less voltage than silicon, hence it will quickly pushing into the conduction state, okay. That's all, right. Which of the following is not a property of an amplifier? Amplifier having property of gain, linearity, distortion also, nonlinear distortion, harmonic distortion. Loss like is not belongs to amplifier. Maybe your transformer, maybe some other elements not belongs to amplifier. So that means we have to select this option, okay. Right. D is a correct option. Zener diodes are used as voltage regulators. Already repeated question. By mistake some questions may be repeat like this. Oscillator has the best frequency stability. Do you remember? The best stability, high frequency are the best out of all. If you find this kind of best, good, quality, high in this, if you find these kind of keywords in oscillator, no second thought, first priority crystal oscillator. Crystal oscillator, okay. Crystal control oscillator or crystal oscillator, of course. If crystal is not available, then high stability means Wien bridge oscillator. Second bit I am giving you. If crystal is not available, definitely they will give you Wien bridge oscillator, okay. Even both are provided, first priority crystal, next Wien bridge, that's all. You see some 1 or 2 questions from digital. This is a latch, SR latch, okay, direct question, SR latch. They are asking just name. It is not a adder, counter or something, it is a SR latch. So De Morgan's theorem states that, look at this, none of the above, if you observe it carefully, De Morgan's theorem, let me write it here. According to the De Morgan's theorem, for example, ABC whole bar, we can write it as what? A bar plus B bar plus C bar. Otherwise, A plus B plus C whole bar is equals to A bar dot B bar dot C bar. The relations from De Morgan's theorem, okay. He has given x plus y whole bar, x plus y whole bar is equals to x bar plus x plus, this is x plus y whole bar, of course, right, x plus y, x bar plus y bar. 1 second, I have selected one question with contradictory. Okay, I think in this model, in the year of 2000, this is 2014, it's okay. 2015, I think one contradictory option was given. As we don't have the time, we may not reach that question if it is available. So, but you don't worry. if this is one and only question found from digital, no option is suitable for that, because they have given some options as it is for the De Morgan's theorem only, but no option was satisfied it. Okay, x minus y whole bar means meaningless. It should be some adjustment, right? A dot b whole bar, I mean x dot y whole bar, x bar plus y bar, this is wrong, okay, this is also wrong. X plus y whole bar, x bar dot y bar, x plus y whole bar, okay, that means it should be x bar dot y bar. It has given x bar plus y bar, so it is wrong. Then what about this x plus y? I think this one only, right? X plus y whole bar is equals to x bar dot y bar, x plus y whole bar, x bar dot y bar, right, this one. So this is also wrong, right? So I thought the question is missing, because intentionally I have selected this question. Question and correct answer, anyone can do it, of course, but here students maybe struggle, why I am not getting any answer, okay? Sometimes it happens. That is the point I want to tell you, right? Just 2 minutes here. So actually it should be like, if it is, if examiner provided it as x bar or x dash, no problem, okay, dot y dar, right, then it would be the correct answer. But there is no option for this. In the key sheet also you can find the star mark for this question, okay, right. Next, any replies from this? I think it's okay, still not working, no problem. So this is the question intentionally I have selected, because from digital I have verified whatever the questions available from the available source, whatever the questions we have from digital electronics, I have verified all the questions. I found only one question with contradictory, no options, okay, no options are correct. And coming to which of the following logic gate is universal logic gate, can be used to construct. Universal means, remember China, you know NAND and NOR gates, okay. Direct questions, sir, you can answer that. Digital electronic questions are direct questions, dead easy questions, 100% no need of coaching. Diploma level fundamentals are sufficient, even not no need of BTech level basics also, diploma level fundamentals are sufficient. Okay, you see, this is a little lengthy question I found, okay, that's why I have selected this intentionally. Only this question you please verify. Xy plus xy bar, this is the expression has given, I am writing it here. What is the final expression? Xy plus xy bar, xy plus xy bar, that means what is the common term here? X, y plus y bar value 1, so f is equals to x. He wants this kind of expression. What does it mean, Chennai? Whenever x value is 1, output should be 1. Whenever the x value is 1, output should be 1. So you see the question, consider the truth table here. Which of the following option A, B, C, D represents, options are A, B, C, D here, represents the function. This function is what? Actually f equal to x. So whenever x value is 1, let me change the color, 1 second. Whenever x value is 1, f value also should be 1. That means output value should be 1. Look at this. This is 0. That's why, sorry, x and that's all, right. So these are the points we need to verify the output. Because of this, I cannot select A. Because of this, I cannot select C. Can you understand what I am saying? C value is how much here? 0. But whenever the x value is 1, output should be 1. Then only I can say this C is nothing but f, like that. Understand? Try to understand this. But sir, this is 1. Yeah, but value of D is 0 now. When, even though x value is 1, this D value is 0. That's why I cannot select D option, C option, E option. But look at this man. What is a B? Value 1, value 1. Whenever the x value is 1. Whenever the x value is 0, B value also 0. What does it mean? What does it mean? B is nothing but x. B is nothing but x. B is following x. He wants the similar function. F is equal to xy plus xy bar means f is equals to xo. That's all. F is equals to x. So which of the functions A, B, C, D are equals to f? That means B can satisfy the f. Why? Because f value x, B value also x. That's why B is the correct option. Right? This is only little, not, I don't say complicated, okay? Little lengthy. Need to spend some time to compare and select the proper option, appropriate option from the table. right? Okay guys, hope you people enjoyed the session. You please type the comments, I will give you the reply, maybe after 1 or half day, okay, right? I will definitely give you the replies, right? All the best, my dear friends.